Hey everyone, welcome to Chemistry 40S. This is lecture number 2 in Unit 2. So let me write that in here. Unit 2, Lecture 2. Okay, and here we're going to look at covalent bonding, whether it's Chemistry 40S, Chemistry 40H. You got to know your covalent bonding. You've seen a little bit of this in grade 10, so some of this will be review. We will look at main group covalent bond formation. We won't use transition metals or intertransition metals. That gets trickier. So we're going to be looking at nonmetals interacting with nonmetals. Hydrogen is a nonmetal, so it is part of covalent bonding situations. Covalent means sharing, like cooperation, sharing of an operation to make something good happen. Hopefully, covalent bonding, sharing of valence electrons between participating nuclei, both are nonmetals. You do use prefixes to name them. Here's some prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca, undeca, dodeca. We won't do more than 10. Theoretically, we have here a hydrogen A and a hydrogen B. They come together, two dots make a dash, and they form a covalent bond. So I'm not going to use the high school dance example this year. That's getting old. We can think of the proton in hydrogen A attracted to the electron in hydrogen A, the proton in hydrogen B attracted to the electron in hydrogen B. You bring the two atoms close together, you get the proton in hydrogen A attracted to the electron in hydrogen B, and the proton in hydrogen B attracted to the electron in hydrogen A. So that attraction causes a covalent bond. You can't get the atoms too close together though, because you also going to get a repulsion, but you're going to get a repulsion between the proton in A and the proton in B, and the electron in A and the electron in B. So you end up with a compromise. If I do look at this diagram on the left here, this is a potential energy versus internuclear separation, the distance between the two nuclei. So when they're really far away from each other, like here, there really is no attraction or repulsion because one atom doesn't even know the other one exists. But as you bring the atoms closer together, they start to talk to each other. And at the bottom of the well, that is known as the bond energy, and that's the most stable energy for the molecule. Remember, the molecule vibrates back and forth around its equilibrium position. The equilibrium position we can represent by r being the distance between the two atoms. Some of you say, oh, we should use d, r is only for radius. Well, no, that's not true. R can be used for distance as well. So r is the distance between the two points, and the equilibrium distance is called the bond length. Being stable means more and more negative in energy. If you squeeze them too close together, you get too positive value, and that makes it fall apart. So you have this compromise, which gives me the covalent bond. That's page 4 in your booklet. Here are just some examples of naming. P4010, tetraphosphorus decaoxide, C2H4, that's a 4. Dicarbon tetrahydride. Notice the empirical form. These are not empirical formula. These are molecular formula. I'm not going to reduce them down for covalent like I did for ionic. There is a reason to do empirical for covalent, but that's for another day and another story. We're going to focus on molecular formula. C2H6 is ethane. That's an organic naming system. You could also call it dicarbon hexahydride, but usually when you get to organics, you have this other naming system, like C2H2 dicarbon dihydride is also called ethine. In the old days we called it acetylene. CH4 carbon tetrahydride would, in the organic system, called methane. And some of you got to organic chemistry last year, some of you didn't, depending on the order of things. If I write something like CO, that's carbon monoxide. Typically, I won't mark it wrong, but typically you don't call it monocarbon monoxide. The first element that you name, if there's just one of them, you don't put the mono in front, but other elements you do. So that is an example, carbon monoxide. CO2 is carbon dioxide, and on and on. Okay? So let's look at some Lewis diagrams for covalent compounds. The rules are different than the Lewis diagrams for ionic compounds. General rules is that hydrogen and the halogens are terminal, so they're at the end of the molecule that you're looking at, and they only form single bonds, so just 2 dots, right? 2 dots is a single bond, 4 dots is a double bond, and 6 dots is a triple bond. Okay? You try to satisfy the octet rule. Hydrogen can't, it's too small, so it's just 2 electrons. Boron can have cases where it's just 6 electrons around it, not 8. And then you can have more than 8. We won't talk about that in this particular course. In the regular Chem 40S, the honors would. Sulfur, phosphorus, silicon, xenon, bromine, iodine, a few others, they can have more than 8, but we won't bother with that for now. We aren't going to have odd numbers of electrons. That's another weird exception. We won't talk about that. Typically, when you write the molecule, you put the more electronegative atom at the right and the less electronegative atom at the left. Now, if there's more than 2 atoms, then there's rules like here, rule 3. Usually, not always, but usually the least electronegative atom is the central atom in a polyatomic molecule. Polyatomic means just 3 or more atoms. So in carbon dioxide, carbon is in the center, oxygen at either side, and what I've drawn here is the Lewis diagram for CO2. But when I just write it like CO2, you might say, oh, the oxygen has to be in the middle because that's like COO. But no, that's not the case. I'm just writing the molecular formula of the carbon and then oxygen and oxygen. But in the Lewis diagram, I got carbon in the center and then oxygen on either side. Double bonds, you have what's called a sigma bond and a pi bond. Triple bond, you have a sigma bond and 2 pi bonds. The sigma bond just refers to electron density focused along the internuclear bond axis, whereas pi bonding is above and below concentration of electron density, above and below the plane of the molecule. So that's just some other nomenclature, but you should know what a double bond is, what a triple bond is, what a single bond is. Quadruple bonds, we don't get to that. Okay, double and triple bonds are most commonly seen in carbon, oxygen, phosphorus, sulfur, nitrogen, and silicon. So let's go on a little survey through some Lewis diagrams based on those rules, and there's a few others that we're going to come across. So start, well, let's not do the noble gases because they don't form much. So let's start with the halogens, fluorine, chlorine, bromine, iodine. I know there's other ones, but these are the ones where there's the most experimental data. So you're going to have an example, hydrogen fluoride. So we've got HF. Okay, there's 8 electrons, 2, 4, 6, 8 valence electrons. You count the valence electrons and then you distribute them to satisfy the octet rule, or in hydrogen case, the duet rule. And the 2 dots or a dash is called a bond pair, or a bonded pair, or a shared pair. Most people call it bond pair. That's the quickest, shortest way to write it. So there's 1 bond pair between the hydrogen and the fluorine. Then the fluorine has 6 electrons that aren't involved in the bonding, 3 pairs, and they're called lone pairs. You say, oh, they aren't lonely, they have the other electron paired with them. Yeah, but they're lone in that they aren't involved with the other atoms. So there's 1, 2, there's 3 lone pairs, or 6 lone pair electrons. Some people call them unshared pairs, unbonded pairs, non-bonded pairs, but lone pair is the most commonly one used. So it's the shortest one to write, so I'm going to use it as well. Okay? Difluorine, which really is called fluorine. Don't call it difluorine. You can, it's not wrong, but it's not commonly done. So the number of valence electrons, each fluorine has 7 valence electrons. So for the Lewis diagram strategy, you just add the 7, 7, so you got to sprinkle in 14 valence electrons. So start with the bond, make it a single bond, that's 2, and then you got 12 left, 2, 4, 6, 8, 10, 12, nicely symmetrical. There's fluorine. I like to finish it off and make a dash between the fluorines. So I got 2, 4, 6, 2, 4, 6. Iodine, there it is, also with 14 electrons. Okay? And I could look at any mix of halogens. I could look at chlorine fluoride, right? ClF. So I got ClF, right? And I don't have to count all the valence electrons for here. Just use the periodic table. I know chlorine and fluorine are in the same column, the halogen column, so you're going to have a similar Lewis diagram than the iodine, than the fluorine. Okay, on to page 6. Let's continue our survey and look at throw some group 6 elements, non-metals, into the mix, or metalloids, which is sort of dancing between metals and non-metals. And the most common ones that have this are oxygen, sulfur, selenium. I guess you can have tellurium as well. Let me check my periodic table there. That tellurium is in the same tellurium, where is it? Yes, it's with the same group, group 6A or group 16, fine. So I can add tellurium, fine. So oxygen difluoride, you're going to have 20 valence electrons. The oxygen gives you 6. Each fluorine gives you 7. So that's 20. So start by making single bonds because the fluorine are terminal, so they go in the end. So there's single bonds, and you got 16 left. So 2, 4, 6, 8, 10, 12, 14, 16. And that is my molecule oxygen difluoride. Okay, fluorine is more electronegative than oxygen. It gets the IDE ending in the naming system. So oxygen difluoride. And it doesn't matter whether I draw it in a straight line or draw it like on an angle, because all this Lewis diagram tells us is what's bonded to what, and is it a single, double, or triple bond. It does not directly give us the geometry. We're going to get to that in this chapter, in the second half of the chapter. But for now, we're just focusing on a valid Lewis diagram, and there it is. SCl2, well, you don't have to really count anything because you just know that sulfur is in the same group as oxygen, chlorine is in the same group as fluorine. So SCl2 is Lewis diagram as we see over there. Dihydrogen oxide, you could call it dihydrogen monoxide if you want. That's probably better. Let's do that. Dihydrogen monoxide. H2O. So you got a hydrogen, you got oxygens, and you have 6 from the oxygen, 1 from each hydrogen. So you got 8 valence electrons that have to sprinkle around to satisfy the octet rule. They do. Hydrogen can't. It's the duet rule, but that's okay. For fun, around the dinner table tonight, ask someone at the table, hey, please pass the dihydrogen monoxide, and see if they know what the heck you're talking about. Okay. Dioxygen, okay, now that is also just called the oxygen molecule. And there, you got oxygen, oxygen, so you're going to have 12 valence electrons. Each oxygen gives you 6. Now, if I try just to make a single bond and put electrons around, I get 6, 12, 14. I can't have 14 electrons. I only have 12, so I have to double things up. Okay, so I'm going to get rid of one there, and you make a double bond. And now the oxygen 2, 4, 6, 8, the other oxygen 2, 4, 6, 8. 12 and 12 altogether. So you have to play around with these to get things to be satisfied. And a common mistake is students just add in extra electrons, and well, you can't do that. You can't just create electrons out of nothing. So that's not a good plan. Ozone is O3. And here there's 18 valence electrons that have to be sprinkled in. So you can have a double bond and a single bond. I could write it the other way, the double bond between the oxygens on the right and the central oxygen. Either way is fine. And next year you're going to get into what's called resonance structure, where the actual the actual Lewis diagram is best represented as an average of these two resonance structures. It's called a resonance hybrid. But for now, either one is valid. Okay, H2SO4, that's an oxyacid or an oxoacid. There, the sulfur's in the center. These are 4s. This is a 4, okay? looks like a 7, doesn't it? Sorry, it's a 4. So there are 4 oxygens around the central sulfur, and then hydrogens are dangling from any of the 2 oxygens. It doesn't matter which one. So you should really memorize this kind of structure because oxyacids are used a lot in chemistry, especially in industrial chemistry. In terms of how many electrons there are, sulfur is 6, each oxygen is 4, and then 2 more hydrogens, so 32 valence electrons. So you sprinkle them out to get 32. Now if you Google this, you may find some double bonds between the sulfur and oxygen, meaning more than 8 electrons. Okay, that's a possibility, that's a bit more advanced. So bottom line is don't Google Lewis structures, okay? Just figure it out on your own. Okay, you aren't going to get numbers much more than 32. You don't need a calculator. You want to use a calculator, go ahead, but you don't need one. Okay, so those are some examples, and you're going to get practice with lots more. Let's continue the survey here. Group 5, nitrogen, phosphorus, and arsenic are the most common elements that undergo covalent bonding in group 5. Ammonia is NH3, that's 8 electrons. Ammonium is also 8 electrons. To get ammonium, you got to put the square bracket in the plus sign. So nitrogen gives you 5 valence electrons. Each hydrogen gives you 1, so that's 9, but it's a cation, so I have to subtract 1, so I get 8 valence electrons. And there we have it. Okay, so ammonia is different than ammonium. What are some other ones here? I got PF3, which looks similar to NH3, doesn't it? Except instead of a hydrogen, you have halogens, but you still just have a lone pair on the phosphorus. So the phosphorus has 3 bond pairs around it. Say phosphorus 3 bond pairs and 1 lone pair. BP for bond pair, LP for lone pair. Each fluorine has 3 lone pairs around it and 1 bond pair. Nitrogen, well, that's triple bond. There's just 10 electrons. You can't just toss in extra electrons. You have to actually get a triple bond to get nitrogen molecule to happen. Nitric acid, whenever you have these, it's another example of an oxyacid, have a hydrogen bonded to an oxygen, single, and usually it's single bonded to nitrogen. So you put a double bond at either of the other oxygens. So this one you're just going to have to play around with and try these other ones. I'll do one with you here. NO3 minus. Let's look at NO3 minus. So nitrogen gives you 5. Each oxygen gives you 6. This is a nitrate anion. You get Lewis diagrams for anions. Polyatomic anion. And then I got one more. Right? Nitrate is known as an example of a polyatomic anion. Nitrogen likes to be at the center of things. Oxygen surrounds it. I'll make 1 double bond, and these guys single bonds. The whole thing I have to put a square bracket. And there's got to be 24 valence electrons. So I got 6, 12, 14, 16, 18, 20, 22, 24. And you can make the double bond between any N and O, and then the others will be single. So in fact, you could have 3 equivalent Lewis diagrams for nitrate. Okay, then we get to group 4. Carbon, silicon, germanium are the ones most likely to have covalent bond associated with them. So here's carbon tetrachloride. You'd have carbon's got 4 valence, each chlorine's got 7, so 28 and 4, 32, 2, 4, 6, 8, 24, 32. SiCl2F2, well, that's easy. Just use the periodic table. You got 2 fluorines and 2 chlorines, and then the silicon in the center. A bit of a weirder one in terms of not quite sure what to do with it is formaldehyde. But formaldehyde, you're going to have H2CO. So this is just one you memorize. This is an example of an aldehyde. So you have carbon in the center. Carbon loves to be in the center. That's why it's cool that it's got the letter C for it. And then you have oxygen and hydrogens on either side. So you have 12 valence electrons. 2, 4, 6, 8, 10, 12. So that's formaldehyde. Here's hydrogen cyanide, carbon dioxide, carbon monoxide. For some reason, carbon monoxide trips people up. Carbon gives you 4, oxygen gives you 6. So now you have 10 valence electrons. So all you do is you take those 10, and now you just find how can we satisfy the octet rule with 10 electrons. You go 2, 4, 6, 8, 10. I think some people, they've learned some other method where they go like a 4 and they do a 6. And then they start crossing things. Don't do that. Forget about that, okay? Just take the 10 valence electrons and sprinkle it in, and away you go. H2CS, well, let's see, we have carbon, and then we're going to have sulfur, and we're going to have hydrogens. Now, I can have them as a sort of predicting what the geometry is going to be like, but I don't have to. But there's H2CS, GeCl2F2. So GeCl, it doesn't matter where I put these atoms which are surrounding the central atom. You need at least 3 atoms to have a central atom. And group 4s like to be at center. So that's the central atom. By the way, the atoms that are bonded to the central atom, they're called the ligands. It's a silly word, isn't it? But the atoms bonded to the central atom are called ligands. And we'll need that in the second part of this chapter. Okay. Here I see a bunch of organic molecules, just a survey where you can have more than one central atom in ethane and propane. Methane, well, they're just one central atom. Ethene, also called acetylene, ethine, benzene, acetic acid. Those are examples of a bit larger organic molecules. And so organic meaning we're using carbon. So those are some Lewis diagrams for that. Cis-trans isomers, let's not worry about that this year. Okay, that's not necessary right now. Mixed species, what's that all about? Ammonium carbonate. Oh, when we talk about a mixed species, what we're talking about is where it's a mixed species, it's an ionic compound, but there's covalent bonding within the cation and or anion. So if I cross this over, I'm going to get NH4 taken twice, CO3. That is the empirical formula for ammonium carbonate. It is an example of an ionic compound. The Lewis structure, which you're going to have 2 NH4 plus, then comma, and then you're going to have a carbon, and then you're going to have oxygens around it. One of them is a double bond, the others are single bonds. So that's 2 minus, and then you have a nitrogen, hydrogen, 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 hydrogen. So 2 NH4 plus, and then CO3, 2 minus. So that is an example of a mixed species, because you have covalent bonding within the cation and the anion, and ionic bonding between the cation and the anion. Sodium phosphate is another example. Sodium is Na+, phosphate PO4 3-, cross them over. So you get Na3 PO4, and I'll let you figure out the Lewis diagram to see that there is covalent bonding within the phosphate. Okay. Electron deficient compounds. Boron is an interesting case. You can get boron with just 6 valence electrons around the boron. Boron trifluoride. You have 3 valence electrons from the boron and 3 times 7, 21 from the fluorine, for a total of 24 valence electrons. So 6, 12, 18, 22, 24. So there isn't another electron pair. And boron can be happy, especially in the gas phase, if it is like this. So boron is an exception. It has less than 8 electrons around it. Bf4-, the boron tetrafluoride anion, that one isn't an exception. It's happy. The boron's got 8 around it. But we do have to think a bit about the boron being an exception, and we'll get into that in a while. Expanded valence, that we're going to look at for the honors guys only. Electronegativity, well, that's going to be in lecture 3, because we've done lots of Lewis diagrams. You're going to get practice. I've got some practice sheets for that. But that's good enough for now for our study on electron, on covalent bonding, I think, ... We get to electronegativity next time.